Hello, everyone, and welcome to the course of EKS architecture. Today, we'll understand how the AWS EKS architecture works. Now, what exactly is a Kubernetes cluster? Now, Kubernetes cluster has nodes. What exactly is a node? A node is a virtual machine or an EC2 instance that runs workloads in form of pods. So, what exactly is a Kubernetes cluster? It is a group of nodes that work together to manage and containerize the applications. So Kubernetes cluster is a group of nodes that work together to manage the containerized application. Now, in the Kubernetes cluster, there are basically two types of nodes. One is the control plane, or what we call the master node, which acts as the brain of the cluster. The second one is the worker nodes, which runs the applications. It has two nodes. One is the master node, and the second one is the worker node. Master node is the brain, worker node is where the applications are run. Now let us take a look at the control plane components. The first one is the Kube API server. Now the Kube API server acts as the entry point for all the commands and communication. The second is the Kube controller manager. Now, what it does, it monitors the current cluster state and compares it to the required desired state. Third one is the Kube scheduler. It acts as a placement officer. It means it selects the nodes where the pods can be best scheduled. Fourth one is the etcd. Now etcd is it's a key value storage. It is a database that keeps track of the entire cluster. So Masternode has four components: the API server, controller manager, scheduler, and the etcd. Now let's take a look at the worker node components. Now first worker node component is the kubelet. Now kubelet is an agent that runs on the worker nodes. It communicates with the API server and manages containers and reports back. Second one is the kube proxy. It ensures the pods can communicate with each other easily. It basically handles the assignment of the IP addresses in the pods. Third one is the container runtime. Now, container runtime is the main engine that powers the containers. It means it is the main thing that makes the containers work. So it has three main components: the kubelet, the kube proxy, and the container runtime. Now let's take a look at the Amazon EKS. What are its advantages? Now the main advantage is the AWS fully manages the control plane, the master nodes. Uh, Second thing, no need to install, patch, or upgrade or maintain the whole control plane. It is done automatically by the AWS. And third thing is it is highly available across multiple availability zones by default. Now let's take a look at the Amazon EKS. So the control plane, including the API server and the etcd, is automatically distributed across different availability zones across the region. Now, this gives you high availability, fault tolerance, and no single point of failure. Now, let's take a look at the Amazon EKS. So your control plane, it lives in the private subnets managed by AWS and is backed by a network load balancer that handles requests from tools like kubectl. So AWS manages the Kubernetes control plane across multiple availability zones. It provides high availability and it eliminates the need to manage the API servers. So we don't need to manage the control plane. Second thing is the single Kubernetes endpoint via network flow balancer. So you install the kubectl, and that is how the worker nodes communicate with the highly available control plane. Now, how do you connect to the EKS? Now, when you run a command using kubectl, it reads a kubeconfig file to locate the EKS API server endpoint and the cluster certificate authority or CA. It then generates an authentication token and sends a secure HTTPS request to the Kubernetes API server running in the EKS control plane. The request is TLS encrypted, and kubectl uses CS certificate to verify the sender's identity before the request is processed. So even if one availability zone goes down, your cluster stays online. That's the power of AWS managed infrastructure. Now, while the AWS manages control plane, you have options for managing the worker nodes, also called the data plane. In standard mode, you manage the worker nodes while AWS manages the control plane. You can either maintain nodes yourself with self-managed nodes or use managed node groups where AWS helps with scaling and updates. These nodes typically run EKS optimized AMIs pre-configured with kubelet and container runtime. Once the nodes are launched, they attempt to connect to the control plane. If everything is configured correctly, such as network access and permissions, they will successfully join the cluster. While this usually happens shortly after the launch, the connection can take some time depending on factors like instance startup speed, network configuration, and cluster permissions. Once connected, the nodes become available to run your workload. Now let's take a look at the auto mode. Now AWS manages both the control plane and the worker nodes. Now in the AWS auto mode, AWS manages both control plane and worker node. It automatically provisions EC2 instances, scales them, applies patches, and handles security. This is great for teams that want to minimize operational overhead. Now let us take a look at the third type, the Fargate. Now, Fargate is the AWS serverless option for running pods. They don't manage any EC2 instances. AWS provisions compute resources per pod. You only pay for what you use. It's ideal for small bursty or event-driven workloads. However, it has some limitations. It has no support for daemon sets, privileged containers, and it does not support AWS EBS as persistent volume. Now, while getting started with EKS, it's important to understand how different components work together. During cluster creation, without a clear view of architecture, it's hard to know what's being set up and why. Now let's walk through the EKS architecture that gets created when we launch a cluster. In this section, in the next, we will focus on how setting up the cluster and the tools required to manage it. As we move forward in the course, we will expand the architecture with additional components like node groups, Fargate profiles, load balancers, persistent storage, and with the advanced networking. Now we start by selecting the AWS region in which we want to create the EKS cluster. The choice determines the physical location of the control plane and the related networking resources. We would be working with US East 2 or Y region. When an EKS cluster is created, the Kubernetes control plane requires permissions to interact with AWS services. To enable this, we will assign a cluster IAM role during setup. This role must include the Amazon EKS cluster policy, which grants the control plane the necessary permissions to manage the EC2 networking, auto-scaling, load balancers, and related resources on your behalf. Optionally, we will also attach Amazon VPC resource controller policy to allow EKS to automatically manage networking resources like IP addresses and elastic network interfaces. We would be using both of these policies for the role in our demo. The control plane in the EKS runs inside an AWS managed VPC, not the one we create. However, it still needs to communicate with a worker node of Fargate profile, which we will make inside our VPC. To make this communication possible, we select a VPC and choose at least two subnets in different availability zones. These subnets are used to launch worker nodes or pods, assigning IP addresses and host ANIs that connect back to the control plane securely. In our case, we will be using default VPC and selecting public subnets to keep the initial setup simple. Now, when you create an EKS cluster, AWS automatically sets up a cluster security group to allow communication between the control plane and worker nodes. Optionally, you can attach additional security groups to the ENIs in the control plane subnets. This lets you define a custom access rules such as allowing or restricting access to the Kubernetes API server via its URL or the cluster endpoint from specific IPs or networks. These additional groups apply only to the control plane and provide extra flexibility for securing API access and meeting environment specific requirements. We will be using default security group, which has all ports open by default, making initial setup and communication straightforward. However, in a more restricted setup, if you are using kubectl from your laptop, you will want to make sure that the port 443 is open in the security group. This ensures that your machine can securely connect to the control plane and issue commands. Now, let's take a look at the cluster endpoint accesses. When configuring access to a Kubernetes API server, we have three options: public access, private access, or public and private access. Now, the public access makes the API server reachable over the internet. It's convenient for remote access, but less secure since worker node traffic may leave the VPC. Now, second we have is the private access. Private access limits the API server to internal VPC access only. It is the most secure option, but it also makes external access more difficult. Third one is the public and private access. Now, this gives us the best of both worlds. The API server is accessible publicly for admin tasks, while worker nodes communicate privately with the control plane inside VPC. This setup balances security with accessibility. In our demo, we'll go through public and private options. Now, to simplify cluster operations, EKS provides several optional add-ons that we enable during or after cluster creation. Now, the VPC CNI plugin handles pod networking, allowing each pod to get its own IP address. The core DNS enables service discovery within the cluster. Proxy manages internal service routing. We also have the metrics server, which gathers resource usage data for horizontal pod autoscaling. Now, the pod identity agent allows us to securely assign IAM roles to individuals, enabling fine-grained access control when interacting with AWS services. This agent needs to be installed externally and it's not included by default in EKS clusters. Now, in our EFS demo, we will use this agent to demonstrate how pods can securely access AWS resources without relying on node-level credentials. And there are other useful tools like external DNS for matching DNS records automatically and a node monitoring agent to track the node health. Now, to interact with the EKS cluster, we have two key components: the command line tools. We start by installing kubectl, the standardized Kubernetes CLI. This tool allows us to run commands like checking pod status or deploy application by sending requests to the API server. Next, we install is the AWS CLI. Now, it helps us generate the kubeconfig file. The file contains everything kubectl needs to connect to the cluster, including the API endpoint, authentication settings, and certificates. In our setup, we are using an IAM user called Harsh to run AWS CLI commands. This user initially has full access, and as we progress through the course, we will grant additional permissions as needed. Now, once the kube config file is in place, kubectl can securely communicate with EKS control plane using the credentials and endpoint defined in that file. Now, EKS also allows you to configure observability during your cluster setup. You can enable metric collection and control plane logging to help monitor your cluster's performance and troubleshoot issues when needed. We will enable a few of these features for demonstration purpose. However, keep in mind that these capabilities come with additional costs, so it's best to enable them only when necessary. Now, once the cluster is running, access control becomes essential. Authentication is handled using AWS IAM. When a user tries to access the cluster, EKS uses their IAM identity to verify if they are allowed to connect. In our case, Harsh user, we are using Harsh user and we provide an IAM access entry for this user. This access entry tells CKS that user is allowed to authenticate and connect to the Kubernetes cluster using tools like kubectl. Once the authentication is set up, two key components become important: the Kubernetes API server endpoint and OIDC provider URL. The API server endpoint is the address kubectl uses to connect to your EKS cluster. All authenticated requests like listing ports or deploying apps are sent through this endpoint to reach the control plane. The OIDC provider URL is used for authenticating pods. It allows Kubernetes service accounts to assume IAM roles, so your applications can securely access AWS services without storing credentials inside containers. Both are created automatically by EKS and play a vital role in managing secure access for users and workloads. Now, this wraps up the lecture. Thank you.